Hello, I'm Yukihiro Tadokoro from Toyota Research Institute of North America. So today, let me talk about the efficient AI-assisted fabrication method for the carbon nanotube-based nanocantilevers. So this work aims to develop the advanced sensing and electromagnetic applications. So this slide shows the carbon nanotube-based cantilevers or nanobeams which is used in various fields like mass sensor, diode, and biosensors. So these devices can provide a very, very nice sensitivity in the sensing and electromagnetic characteristic in the electric devices. And recently, so we can find a nice digital image transfer application with this very tiny nanoscale cantilevers in this work. And also, this kind of device can be also used as electron sources like this one. To develop this type of the nanoscale devices, so we need to make these devices with the nanoscale fabrication method. So this picture shows our typical fabrication process used in our lab. So here you can find the fabrication of the carbon nanotube cantilever based on the existing semiconductor processes. So the cost of the fabrication is a little bit cheaper, but we have to consider how to develop this tiny structure. So in a setup, so we at first we place the carbon nanotube by scattering on the silicon dioxide layer because uh, it's pretty hard to manipulate the single carbon nanotube. Yeah. So in this case, so maybe on the silicon dioxide wafer, so there are so many carbon nanotubes, but we don't know where it's located. So to develop the cantilever structure, so we need to place one edge by the maybe electrodes. So to achieve it, so we need to know where it's located. And then, so if we got the information, so we can make the CAD file to make the electrode on the edge like this one with the E-beam lithography or something. And then we can make the cantilever structure or nanobeam structure like this one. But the problem here is that how to know the position of the carbon nanotube and which edge is suitable to place the electrode. So in our previous steps, so it takes so much time to measure the position of these randomly positioned carbon nanotubes by using the observation of the SEM images like this one. So to solve this problem, so we develop AI-based fabrication method. So to efficiently fabricate massive field emitters with carbon nanotube-based nanocantilevers like this one, so we introduced a semiconductor process-based method that utilizes artificial intelligence. So in the previous method with manual observation, so it takes several hours, but according to this nice AI-based method, so we can significantly reduce this designing speed to 2 seconds. It's a huge progress or improvement. And in this talk, so we also show application of the CRT-based field emitters like this one in recently developed neuromorphic computing. So this behavior with the field emission can be used as a physical activation function. This function is a key component in a deep neural network. Okay, so next, this slide shows the designed nanoscale structure to make a carbon nanotube-based cantilever. So this is a cantilever, carbon nanotube, and here you can find the two electrodes of the cathode and anode. At the one edge of the carbon nanotube, you can find the nanoscale gap with the length of the 80 nanometers, and to the counter electrode of the anode. Yeah. So according to this tiny space, so the tip of the carbon nanotube can vibrate. Yeah. So according to this designing, so we develop the AI-based fabrication method like this one. So at first, so after placing the carbon nanotube in a random manner, so we take the SEM images showing the marker and randomly position the carbon nanotube. So this means that so each picture contains maybe several carbon nanotubes and one marker. So these images are inputted to the deep neural network, so-called faster RCNN. And so this deep neural network can recognize the CNTs and measure the position and label. So this label contains which H is suitable to place the electrode to form the cantilever. Yeah, so this output contains this kind of the information, and based on it, we can CAD file, which will be used in nanoscale fabrication like e-beam lithography or something. Okay, so this CAD file is automatically created by originally developed Python code. It's quite fast. So according to this automatic process, so we can significantly reduce the designing speed from 20 hours to 2 seconds. Yeah. So next slide, let me explain what is a faster RCNN and how to obtain the important information of the recognized CMTs. So this deep neural network, fast RCNN, is a two-stage object recognition method with CNN, RPN, and classifier. Yeah, this method was developed more than 8 years ago, and this neural network shows outstanding capability in terms of the recognition, position measurement. And interesting point is that two types of the output, so position and labeling, can be obtained from this neural network. So this characteristic is quite nice for our purpose because we can obtain the recommended edge for fabricating the anode can be obtained as the label, and another important information of the position of the recognized CLT is obtained as a bounding box. So in the bounding box, so we can have the information of the four corners, this one, this one, this one, this one. Yeah. And so two corners should show the position of the two edge. And according to this information, so we can know where the carbon nanotube is located. And another information of label shows which edge is suitable for fabricating the anode. Yeah, so this kind of information obtained here. So the detail can be obtained in this picture. So bounding box has four corners. So if we can have this label, which shows that this corner is suitable to place the electrode of the anode. Yeah. So this slide shows how we can obtain the dataset for training the first RCNN. So to get this dataset, we fabricated about 14 test samples. and we manually observe the position and edge of the anode is measured or determined to make this kind of the data set. Yeah. So this task is quite tough, but we successfully make this data set. And by using this one, we train the neural network with this amount of the sample and then test it with 93 samples. But to train the neural network efficiently, we use the previously learned neural network by VGG16. So for the image recognition tasks. Okay. So next slide shows recognition performance by using this neural network. So we've tried to fabricate the carbon nanotube-based cantilever and manually inspected 96 samples by using SEM images to evaluate the recognition error. So in this picture, you can find the definition of the recognition error. So in this box, we assume that the recognized CLT has the shape of the straight one, this one. But unfortunately, the CLT is somewhat bended like this one. So we can observe some error at each edge, this one and this one. So this error was measured manually, and here you can find the performance of this error. So this figure shows that the 6% of the recognized CLT has the error within the 150 nanometers. So this number is quite important because here you can find the design structure of the cantilever, and this width of the counter electrode is 300 nanometers. So the half of this width is 150 meters. So if the chip is located within this range, so the chip is very close to the counter electrode. So it's okay to form the cantilever. Okay. But unfortunately, according to the nice performance of the neural network, so we can obtain the 60% of the recognized CLT can be pressed very close to the counter electrode. Yeah, and then another figure shows the distribution of the fabricated samples in terms of the lengths and gaps. And so another key point of nano gap has a significant influence to the performance of the period emission. So, and our current designing has a nano gap of the 18 nanometer here. And this figure shows that this characteristic take a peak around the designed value for the nano gap and even for the length of the cantilever. So in average sense, so we can successfully fabricate the cantilever to the designed structure. Okay, so next, so let me show the evaluation result of the fabricated devices. So, so this type of the cantilever can be used as a field emitter. So we measure the field emission performance to evaluate the fabricated devices. So to do it, so we at first apply the DC voltage between the two electrodes here and here. And then we measure the resulting field emission current, IFT. This measurement was conducted in the vacuum chamber with a vacuum pressure of this one. Okay. So the expected result is that according to the traditional forerunner theory, so we can observe the exponential behavior in terms of the applied voltage. Okay, so this is the result of the measured field emission performance. So we measure this performance with 9 samples. And unfortunately, we can find the deviation on the average curve, this one. So this deviation should be caused by the structural variations, mainly nanogap length. Because as I mentioned in this slide, so in average sense, so the fabricated sample is very close to the designed value, but many samples has a little bit different from the designed value, you know. So this structural variation causes this kind of the fluctuation or deviation. Yeah, but so here this red curve shows the theoretical value which was calculated from this theory. And here you can find that the behavior of the measured result totally follows the theoretical curve. So this shows that we can successfully make the fabric field emitters. And the next, so let me show what can be used with this massive CNT-based cantilevers. So recently, nice computing platform of the neuromorphic computing has significantly discussed. And this type of the new computing platform can be achieved with a physical system like uh, MEMS or memory stars and something. So here we can show this kind of cantilever can be used as a physical activation function, which is quite key component in the neural network. Usually, so as a activation function, the rectified linear is used. But if we use exponential behavior in the field emission, can be used as a rectified linear because as you see in these pictures, so we can observe the quite exponential. It's kind of the switching two-state system. So this behavior is quite suitable for the activation function. So we emulate this structure or a neural network with the measured data like this one, and we test the image recognition task with the MNIST data set like this one. So here you can find the prediction accuracy in this table. So if we use the traditional rectified linear function as an activation function, the accuracy is about 97%. But if we switch to use this physical activation function with the common nanotube-based cantilevers, so the accuracy a little bit goes down, but it still takes a high number of the 9%. So this number shows the capability of using this nanocantilever as a physical activation function. Okay, so let me conclude this talk. In this talk, to efficiently fabricate massive field emitter with CNT-based nanocantilevers, we introduce a semiconductor-based method with artificial intelligence. So this method provides a very fast designing speed in second order, and it also provides a nice recognition and device performances. And now we'll also show the application of this massive field emitters to the neural computing. So you can find details in the published paper in one of the Nature Family journals. Okay, thank you for your attention.